welcome. Today, as the title suggested, I am going to be making a video covering another integration technique, integration using partial fractions, and it's going to be a great time. Let's get started. For those of you new to integration using partial fractions, here's a list of skills you should either be able to do or be willing to work on until you have a good solid idea of how to do them. If you're like me and need to brush up on a few things, I'll have links to a couple videos in the description detailing what's listed here. So here are the two examples I'll be covering later on in this tutorial. I've chosen these specific examples because, like the photo says, one is pretty simple and the other one includes a few extra steps. But don't worry, I'll walk you through some guidelines to prepare you before we get there. Also, feel free to pause right here to copy these down on a piece of paper for later. The first step in using partial fractions is determining what situations call for it. We use this technique when we are dividing two rational fractions. We do this to break down big, clunky functions into smaller bits that allow us to integrate more easily later. So after determining that partial fractions is necessary, the next step you'll need to take is determining what the powers of the two functions you're working with are. To use partial fractions, we must make sure that the numerator has a lower power than the denominator. In cases where the numerator has a higher power, we use polynomial long division to help sort that out. That creates a lower power function and makes it simpler to break apart later. So, if long division is not necessary, you'll need to make sure everything in the problem is completely factored. Once you've done that, it's time to use the four standard cases to help us break apart some functions. Case 1 is when we have two distinct linear functions presented. And a quick note before we get started, this is the only case that I'll be solving all the way through. In the next cases, be sure to refer back to this if you need a reminder of how to do something presented. Okay, so as shown here, we have x over x plus 3 times x minus 2. First, we'll use a standard ABC format to break apart each of these factors, assigning basic variables a and b to each. Next, we'll multiply it by a common denominator and get rid of the fractions and create a simple algebra situation, allowing us to solve for a and b. At this point, we have x equal to a times x minus 2 plus b times x plus 3. This is where we throw it back to basic algebra. In order to isolate and solve for a and b, we'll need to choose two x's that make each variable go to 0. I do this in two separate steps, but at the same time. Please pause here to take a closer look. The last step in this process is to plug the a and b values we just solved for back into the original ABC format from the beginning. At this point, if it all went well, you'll have some smaller functions that are easier to integrate, and you'll be merrily on your way. Case 2 is similar to Case 1, except there are repeated functions. The example for this one is 1 over x squared minus 4 times x minus 2. Here we have the opportunity to factor down a little bit, and you end up with 1 over x minus 2 times x plus 2 times x minus 2. X minus 2 is repeated, so we're going to write that as x minus 2 squared. From here, we'll put these into our ABC format. In order to make this all work out in the end, we'll need to walk the powers up. That means that when we have repeated factor, we'll need to allow for a variable for each power noted. That sounds a bit confusing, but just take a look. In this example, we have x minus 2 squared present. So, under a, we'll have a plain x minus 2, and under our b, we'll write x minus 2 squared. If our factor was to a third power, we'd write x minus 2 cubed under c, but since that's not the case here, we'll drop our last factor, x plus 2, under our c. From here, you'd isolate and solve for a, b, and c algebraically, plug those variables back into this big equation and integrate. But for time's sake, let's move to Case 3. In Case 3, we have irreducible quadratic factors, none of which repeat. Our example here is x over x minus 2 times x squared plus 1 times x squared plus 4. Like it were planned, you'll notice that they're quadratics. So what we'll do here is simply plug each factor into an ABC format, but we need to make sure that there are two variables over each of the quadratics. After we've reformatted, we'll solve for a through e and plug all of those numbers back in right here before we integrate. We've arrived at the last one. So hopefully you're noticing a trend here. Case 4 is basically Case 3 with repeats. So, like we discussed in case 2, we'll need to make sure we're walking factors up under separate variables. I won't talk through this one in depth, but definitely pause to take a look at how we break this into ABC through H format, and like the rest of the cases, after this, we'd plug in and integrate. To really help drive this skill home, let's pause here and try this one on our own. If your answer looks anything like this, good job. If not, it's all good. You can always go back and rewatch. Example 1. In this example, we are asked to find the integral of x over x squared plus 3x plus 2 with respect to x. So here, the first thing we're going to do is we're going to factor our fraction. The factors of x squared plus 3x plus 2 are x plus 1 times x plus 2. Next, we'll set that equal to our ABC format. So we'll put one of the factors, x plus 1, under A, the other one, x plus 2, under B. The next step in this is to multiply by a common denominator to eliminate the fractions in this problem. So what we end up getting is x equals A times x plus 2 plus b times x plus 1. From here, we are going to choose specific x's that will isolate each of the variables. So in this case, I'm going to choose x equals negative 2 and x equals negative 1. Take a look at the algebra here and feel free to pause to figure out how I solved for both a and b. After this, we're going to plug our a's and b's back into the original function that we had the a's and b's in at the top, and we will integrate. Alright, so this one is a pretty simple one to integrate once you get going. What I want you to notice is that I pull the 2 out because it's a constant, and I end up with integrals that look familiar, and 1 over x, when you integrate that, will become the natural log. So when I pull both of those out, it becomes the negative natural log of x plus 1 plus 2 times the natural log of the absolute value of x plus 2 plus c, because it is an indefinite integral. Congratulations! You've made it to the last example of this video. Let's do this. We need to integrate x squared plus 2 over x plus 1 with respect to x. This is interesting because the numerator has a higher power than the denominator, so we'll need to employ our polynomial long division skills to work through this one. Like I said earlier, if this is a skill that's buried deep in your subconscious, feel free to go click through some videos to get reacquainted and join up back here after you're finished. If you're here, I'm assuming you're already a long division master, so we'll breeze right through this and move to the good stuff. After dividing the polynomials, you'll get x minus 1 plus a remainder of 3 over x plus 1. From here, let's separate our integrals to simplify. And as you can see, the problem has boiled down to some very, very basic integrals. The integral of x dx becomes x squared over 2, the integral of dx becomes a simple x, and when we pull the constant 3 out of the last integral, we're left with 3 times the natural log of the absolute value of x plus 1. And don't forget, this is indefinite, so we'll add a mystery constant at the end.